Up next, for the final section of Billion AI 2021, we are joined today by Dr. Mubarak Shah, UCF Trustee, Chairperson, Chair Professor, and Founding Director of the Center for Research in Computer Visions. He's going to talk to us about advances in computer vision, employing deep learning. Let me quickly introduce Doctor to us. Dr. Shah is a fellow of the IEEE, the NAI, the IAPR, the AAAS, and the SPIE. He's also a member of the Academy of Science, Engineering, and Medicine of Florida. He has published extensively on topics relating to visual surveillance, tracking human activity, and action recognition, object detection, as well as categorization, geo-registration, visual crowd analysis, etc. He is the recipient of ACM SIGMM Technical Achievement Award, also ACM SIGMM Test of Time Honorable Mention Award, the International Conference on Pattern Recognition 2020 Best Scientific Paper Award. I could just go on and on. We are so glad to have you with us today, sir, to address our audience. Over to you, Dr. Shah.
Okay, thank you. Thank you very much. So let's try now, see if it works. Okay, so can you guys see the screen now? Can
no,
you
doctor,
see the slideshow?
No, it's not slideshow yet. It's not.
Okay, so tell me what to do now. Because we went through earlier, right? So you had some changes.
Yeah, doctor, you can stop sharing the screen.
Okay. Shall I try?
You can open PowerPoint, make it full screen.
Yeah, this is open like here.
Yeah, you can make it full screen, and on the Zoom, you can share the full screen view.
Okay, so Zoom screen 1. Do you see now?
Yeah, yes, this is perfect. You may continue.
Do you see the slide version
Yes,
of
yes.
presenter view? Okay. Okay, thank you. I'm happy that it works. So thank you for inviting me. I'm pleased to be here. As I was introduced, I'm going to talk about computer vision, in particular advances in applying deep learning. So I've been working in computer vision for a long time. And so I thought to start with kind of compare what we used to do in classical computer vision and what we are doing in deep learning. So classical computer vision, we used to solve problem in a modular fashion. And we will encode expert knowledge into constraints and then convert constraint and object functions. And then we will optimize the objective function. But in deep learning, what we are doing, we emphasize end-to-end. We don't really do modular fashion. And it has a real learning. And it's, of course, motivated by neural networks and requires label or annotated data. And we need to define a loss function and requires massively parallel computation and uses very simple optimization called gradient descent. But the main thing is that the results are excellent. Actually, things really work. So what I'm going to do next few minutes, go through 10 different problems in computer vision, which we have solved and using deep learning. I'm not going to go through how we solve it, but I'm just going to show you results to appreciate, where's the state of art. So the first problem is person re-identification. So the idea is that, you are given, you want to retrieve an image of a person from a large gallery, and you want to re-identify that. So we have a query image and we have gallery image, and they may be captured from different cameras. And so it's, in a way, it's a cross-camera association problem. So here's an example of this data set we are going to use. So we have, about 1,300 or so people in this, and each person has at least 2 disjoint views, and we have about 13,000 person in this gallery. So as you see that, these people we are shown here are different viewpoint, different, female, male, and so on. So we have a method which works pretty well. So given this query image, and we can retrieve these images, and all of them are correct. Green means all of them are correct. As you see, is a very different query, is a different viewpoint as compared to what we have. Another example, very complicated occlusion. There's a 2% actually, and then we can retrieve like this. Same one here is even more complicated. We can retrieve. So most of the first retrieval are good, but we have one incorrect one, and the last one are also incorrect. And the same phenomena with this one also. So this is the person re-identification. Now, next thing I will show you multi-object tracking. So here the idea is we have a video, and we want to detect objects, and then we want to do data association. We want to track them. So we have this very nice method, which can track people. As you see, there are lots of people, each person in different color, and we can actually track them, and there are crowds and all these kind of things, occlusion, and works well. So this is another example where we are tracking vehicles. There are trucks, there are buses, and so on, and it works also pretty well. So we are showing the track, how this is changing, and the bounding box of that. So now this was a 2D tracking, so which is regular RGB video when you use. But now there's a lot of interest in 3D tracking, especially self-driving cars and robot navigation and so on. So we have extended this method to track the 3D objects and using the LiDAR data. LiDAR provides you the point cloud, and we can actually do that. So this example that we can track the cars here. As you see that we have now 3D bounding boxes instead of 2D bounding boxes. These are the point clouds. And then we have here, we are tracking actually pedestrians, and each one has 3D bounding boxes. Again, if there's occlusion crossing over, we can do pretty well. So now the previous videos were by a fixed camera of observing the ground objects. Now there's a lot of interest in drone videos. As you know, drones are used in agriculture, entertainment, military, surveillance, and sports, and in the wildfire, and so on. So now I'm going to show you one example where we can detect objects, very small objects, from the aerial video. So this is a very wide area video, which is in the Columbus, Ohio, around Ohio State campus. And the problem here, we want to detect these little vehicles, and each vehicle is actually simple points. So we have this result where we can actually detect those. As you see, the ground truth is a green point, and then the circle is when we are detecting. A very few we are missing, but it's a very good results. Next thing we can do is detect drones from drone video. So actually, we call this Dogfight. We had a paper this year, CVPR, and this is the kind of results we can get. So ground truth is shown green, and then red ones show our detection. As you see, these are very complicated, videos, and this also we can do in this case also. So now, other thing we can do is detect anomaly. As you know, that there are so many videos, and every day there are many, many cameras being installed. Now, nobody is there to watch them. There's not enough resources. So what happened, the most of the time things are okay, but very occasionally there is some anomaly, like arrest, arson, burglary, stealing things, assault. So we want to come up with a method which can detect anomaly. So we have a method which will give you a score, anomaly score on this. And suppose this video, whenever there's explosion will happen, then this anomaly score will go very high. and we will know, well, in this video, there's anomaly, unusual event. So there's another example. We have a road accidents. Another example, shooting. So we will get an idea that what videos are normal. Now this is normal. We are playing fast just to save time, but there's no anomaly. It's a regular and a store. So that's about anomaly. Now, in that case, we were saying, is it normal or abnormal? But now, next thing is that we want to know what activity is being performed, what's the action in the video, and we want to also localize that. Where is the action happening? So this is the work where we can recognize these actions. So green is a ground truth, and red is our detection. So say there's a horse riding, there's a diving, there's running. These are different activities, and we can do pretty well. We know where exactly that action is happening. And there's a more example here, picking, climbing stairs, and so on. So now another problem we can solve using deep learning is that we can segment objects pixel-wise, very fine segmentation. So here's an example of each single objects. And these are amazing results. If you had asked me, say 10 years ago, that can we do this kind of segmentation automatically, I say it's impossible. So it is really amazing to see these kind of results. So here we have some multiple objects. Here you can see that there are 3 objects, and there's 3-4 sheep here, airplanes, and all of them we can actually do a pretty good job on this. So the next thing we can do that, well, we are given a text, and based on text we want to segment. So here's an example. We have a sentence: a person is walking backward while being followed by a dog. So based on this, we can actually segment the person. Then we have another sentence: a black dog is crawling. So this is a segmentation of that black dog. Here we have 3 sentences: baby crawling in a corridor, which is shown in green, and the dog on the right is crawling, which is shown in yellow, and the dog on the left is crawling, which is shown in the blue. So these are the videos. So there's a ground truth, and we can see segmentation of these. And the sentence is baby in white is climbing the stairs. So it's amazing that, given a sentence, we can actually segment that. So here we have 2 sentences: baby sitting on the ground and pink ball rolling. As you see, we can actually segment that. So the next thing is this work deals with that we want to do image matching. That's a basic operation we have in computer vision. Especially we are going to apply this, what we call the problem of where am I? Let's say you get lost and GPS doesn't work. The deepest night area, like New York, and very tall buildings, GPS doesn't work. So we have a way to, if you take a picture from your cell phone, then we have a data set where we have the geotag images. So we want to match your picture with the geotag image, and we can tell you that where you are. And this particular picture happened to be in Pittsburgh, and this is the GPS location, longitude, latitude. Now we want to do even harder problem, that we want to do cross-view geolocalization. So our reference is aerial images, and the query is the ground image, panorama. So given that, we want to find out the match, and this is a match, this is the best match, and we can geolocalize within 0 meter. So which is, amazing. I mean, these images are taken a long time ago. This is a color image, and this one we can geolocalize within 2 meters and the 4 meters and so on. So next thing we have done is the work on assessing the damage. So this is the data set which is related to human aid and disaster relief, and they collected this 19 disaster events like floods, volcanic eruption, earthquakes, and hurricanes across the world. And we have these high-resolution satellite images, and we want to label those, each pixel in that, in the 4 categories. So here is the ground truth. So each pixel label one of those four. As you see, red will be complete damage and building, pink is building with major damage and so on. So we have a method which actually give you this, and it's very close to the ground truth, and we actually participate in contests and we did pretty well. So next thing is that we want to retrieve face images with attributes. So let's say, we are given a query like this, and this is typically you can retrieve these images, that's similar to this guy. But we want to do more, and we want to be able to emphasize certain attributes or change attributes, and we want to be able to retrieve. So this method actually we presented a couple of weeks ago in ICCV. We want to adjust the facial attributes and also assign the preference to different attributes. Okay, so here are the results. So given this query, then this is what we typically retrieval you will get. These are the best matches from Celebrate. Now we want to emphasize the bornness. So we want to get the other images where these people are born. So this is the next one. So that's one of the attributes. Here we want to make it smile. We want to remove the smile, and then these are the images. Okay. So another example, we have a query like this, and these are default results. So there's no attributes. Now here we want to make it. We want to get the retrieve images where we have bangs on these women. Then we want to say, well, let's only show only the one with black hair. So these are the results of that. Then we want to say, well, let's get those images with the eyeglasses. So then these are the results. So there are different attributes we can manipulate, and we can do retrieval, which is very, very useful. So the last thing I want to talk about, that one problem with deep learning is it's called black box. So it works very well, as I said, but the problem is we don't know why it's working. So that's why there's a theoretical work people are trying to do what's called postmortem. So it works now. Let's look at each pieces and see what's the problem. So that's also related to grounding. So we are going to look at this problem of visual question answering. So let's say we have an image like this, and we have a question: are the black horses to the right of the vehicle on the road? So typical system will say yes, which is true. But our method, which was in CVPR in June this year, that we can tell you how the system came up with this answer. And that answer is yes. And we say, well, we found the horses, black horses, and also the vehicle, and that's the reason it came up with that. Another example, the question is there's a cube that is in front of blue rubber cylinder. Is it the same color as a metal sphere? The answer is false. That's not true. But we can put a bounding box on those two objects where the system reason that, well, it should be false. Okay, so we saw that there are so many different problems we can solve using deep learning, and results are amazing. Now let me go to the first slide I show you. So now one problem, as you see, that I mentioned that deep learning requires labeled or annotated data. So that's a big problem, and actually all these people are companies spending lots of money just to label. And their company, their job is only label data. So now in order to not to avoid the label, because when the label is called fully supervised. So there are methods which can avoid label. One approach is called semi-supervised, where we have part of the data labeled, very small percentage, but the rest is unlabeled. And the question is that how can you leverage this to actually train the system? So that's a pretty active area. Actually, we had a nice paper this year in iClear, which uses a pseudo labeling idea. The next thing is that, well, labeling is expensive, so can you learn using very few examples? And that's called few shot learning. So what we do, we train a model on a set of base classes, or we have labels, but then we want to adopt that, transfer learning to novel classes with only very few examples. So we had a paper in CVPR this year, which does that and works pretty well. Then the last thing is that you don't have any labels. It's called self-supervised learning. So here we want to train a model completely on unlabeled data and learn the representation, and then this representation learn implying some pre-test tasks. And then once we have learned, then we can fine-tune on downstream supervised tasks. And this also, we have a nice paper here on arXiv. So now other problem, as I mentioned, is that it requires massively parallel computation. Lots of GPUs and so on are needed. So there's a very nice article this month of IEEE Spectrum talk about that how far we can continue with deep learning. So deep learning is diminishing returns. Because the question is, is it sustainable? Can we sustain this? So for example, when everybody saw that DeepMind's system can beat the champion of Go, but it cost $35 million to train the system. There's a lot of talk about every day there are articles about GPT-3 from OpenAI. Now to train that system, it costs $4 million. So so there is the cost, and there's also computing resources. And for example, if you want to take the ImageNet and reduce the error to 5%, then it would require a lot of resources and lots of computation. So this is the computation in floating point operation, billions, and we will be around here, 5%. This is the percent error. But not only that, but this emits a carbon dioxide, and that creates a problem. So this will be equivalent to the carbon dioxide generated by New York City in 1 month. So that's the kind of alarming issue we need to be aware of. So therefore, we need to look at different alternatives, frameworks like analog, neuromorphic computing, optical computing, quantum computing, and so on to continue this kind of progress. So thank you. That's the end of my talk.
Thank you so much, Dr. Shah, for that. Very, very, very interesting and cutting edge stuff that you guys are working on. Brilliant. Thank you so much for joining us, taking time out to address our audience today. Really appreciate it.